So I'm going to talk about, as Tom said, atomistic and continuum approaches to nanoscale crystal plasticity. So actually, I was thinking when I was putting the slides together that actually I'm going to go all the way back to stuff that I did in my PhD, and some of that I thought about in IPAM. So it's very nice to be back here. It was a really nice visit during my PhD, one of the most useful times, I think, when I was out here. Lots of ideas flying around, so it's nice to be back again. What I'm going to talk about is work over a whole swath of my time thinking about dislocations in particular. And so lots of people are involved, people that have passed through Warwick at various points, are still at Warwick in the case of Philip, and also Mark Pelletier and Patrick Vermeers, who are at Eindhoven, or were at Eindhoven. Mark Pelletier still is, Patrick is now in Japan. So I'm going to start slowly, given that it's Thursday morning, and we've been going for a few days now. So as you all well know, in crystals, the process of plasticity is really the process of slip in some sense. So you can see that from this actual optical micrograph of cadmium. So this is a rod of cadmium that's been put into a testing device and pulled. It's undergone plastic deformation, and you can really clearly see, even in the optical micrograph here, the slip planes that have been activated in the process of plasticity. And so what has been understood for a long time now is that the mechanism that causes this process of slip is the motion of dislocations through crystalline materials. And so we know that they are line defects, and in some sense they're the boundaries of the regions of slip. So these, as these slip planes move, dislocations form the edges of these partially slipped planes, if you like. And so moving these dislocations around in lattices is essentially how crystal plasticity occurs, at least inside single crystals. Of course, there's all the complexity of polycrystalline materials that you would need to think. So I'm going to talk about some mathematical models of dislocations. First of all, I'm going to talk about some kind of atomistic models that or inspired atomistic toy models where we can say some things mathematically, and I'll explain how I think that is relevant, even though these are toy models, to suggesting things that are maybe of relevance to computational scientists as well. So where I've got my own version of this diagram that we've seen many times this week already. I tend to operate in what I'm interested in at this kind of level, so somewhere between atoms and continuum, which is a little bit of a challenging area because we have these two phenomenologically different theories. In molecular dynamics and density functional theory, right, we have nuclei and electrons in the case of DFT, so we have really discrete particles, and up here we have fields and continuum PDE models. And so bridging this gap is a little bit of a challenge just because of the phenomenological difference between them, but that's what I'm going to talk about. So what I'm focusing on in this talk, and I've packed quite a lot in, so if there's discussion, we'll see where we go. But the aim is to talk about connections between atomistic models and dislocation dynamics, and then possibly at the end of the talk, actually about dislocation dynamics as a theory itself, discrete dislocation dynamics. Okay. So to start with, I'm going to talk about a toy model that I started thinking about, as I say, in my thesis work. And so the idea is to try to model screw dislocations in some very simple model. And so the way that we thought about this in my thesis is basically to consider, let's say, a BCC crystal, where we know that 111 screw dislocations are a thing, to think about that lattice where I look down the screw dislocation line direction. So that's also the direction that the Burgers vector lives in. And basically to just move kind of columns of atoms in that lattice vertically along this screw dislocation line direction. And so to allow, so I'm not allowing any kind of in-plane relaxation, I'm really just moving these columns up and down. So I'm really kind of thinking of the columns moving rigidly, like you see in this picture. So if you think of a 2D plane, that's what these grey dots are behind. Pardon? Anti-plane shear. Yes, exactly. This is exactly what I'm doing. I'm doing an anti-plane shear model in a lattice. And so now if I think about so if I think about a reference atom on one of these columns, I can kind of assign to every point in this 2D lattice, I can assign a kind of a change of reference height, yb, y psi in this case, or y zeta. And then I can think about, well, if this was my reference atom in this column, and this is my reference atom in this column, well, then I can just say, well, what's the difference in height between these two things? And that gives me this dyb. So that's indeed what you just said, anti-plane motion only. And I can construct a finite difference operator on the heights between my reference atom operates on these columns. Okay, and in this toy model, I'm just going to assume that nearest neighbor columns interact only. Okay, so obviously in reality that's not true, because I'm saying that basically this atom interacts with every other atom in this column, potentially, when I write down a potential, but it does not interact with anything in this column over here that's represented by this grey dot. But for the purposes of doing some mathematical analysis, it's already hard enough to work with this model. So then what I'm going to assume is that there's some periodic interaction between columns. So I have some potential of interaction, which is a bit like if you're familiar with a Pals-Nabarro model. This is very similar. I have a periodic potential that basically should be minimized when I'm in the reference lattice, and when I go away from the reference lattice, I should increase in energy, right? So I'll get some periodic potential that looks something like this, and because this is a toy model, we can basically make this look like whatever we want, really, just to get some intuition. But I mean, any perturbation close to 0, so I'm really going to put in the column difference height. So if I'm close to the lattice, I should expect that I'll get some quadratic behavior that looks like the elastic coefficients, like the shear modulus, right? Is basically what governs the kind of the second derivative at the bottom of this well. Okay, so what I'm going to consider is this energy, and what I do is I will sum over all pairs of nearest neighbor columns in this lattice. So here B is really a pair, an ordered pair of nearest neighbor columns in the lattice, and then I sum up this energy of interaction per unit height, if you like, for the change of height in these two columns, and then that gives me some energy that I can start to think about. Okay. So now I said we want to, so that gives me some energy, but I want to actually think about dislocations in this model, and so I need to have some understanding of what a dislocation is. And so here the idea is to be inspired a little bit by the idea of elastoplasticity in some sense. So first of all, because I'm a mathematician, I'm going to scale my unit so that my lattice spacing is going to be 1. So I'm scaling that away. So this vertical difference between these atoms in whatever units I'm using is going to be just 1. And so now if I look back at this picture of these two columns, so I've got reference atom on one column here and reference atom on another column here. And dyb is the difference in height between these two adjacent reference atoms. What really matters, if I look at this and think about this as two columns of atoms, is for the purposes of working out what atom is next to what, it's not actually dyb, it's dyb where I kind of minimize out over all possible lattice displacements. So by any integer displacement vertically, right? So that's what I can kind of define as an elastic strain on this pair. So if you give me dy, I might have something that's like 1 and 1.25 here. And really, if I kind of recalibrate that and think about what, if I just consider these two columns on their own, the nearest atom vertically is actually this one, which is 1.25 minus 1, right? So, and this beta is exactly that. So it's, I'm saying I take dy, and then I take out any integer part. So I basically round to the nearest integer, and that will give me the elastic strain in this bond. So yeah, the inspiration here, like this is, we formulated this, but similar ideas have been thought of in terms of, say, earlier work by Aritza and Ortiz, where they propose some kind of model that is inspired by that idea. But also, I mean, I originally came across this idea in the work of Wittek, where he used differential displacement maps to really think about screw dislocations. Yep.
Actually, it's a much older problem. There's work by Chel and Plutanis in 1970s.
Okay.
And Ishioka worked on this problem. So there's
okay.
It goes way back into.
You have to give me more references and I'll put them in. Yes. Okay, so how do we make sense of the Burgers vector? So as I said, we can construct, for any pair of columns, I can construct beta by just taking dy and modding out the integer kind of difference in heights. And then I can actually think about what this means physically. And if I take a kind of discrete curl around some triangle, say if I'm this 2D lattice, if I project BCC, I really get a triangular lattice. What I will see is that the curl, the discrete curl where I sum beta around a loop that's oriented, can only be -1, 0, or +1. And you can think about why that would be the case, but essentially it's because I've taken dy and added or subtracted integers on each of these bonds. And so when I sum around a closed loop, I must also get an integer. And because there's only 3 and they can only be between -1/2 and 1/2, I must have an integer between -3/2 and 3/2. So that means that I can essentially just get on each triangle +1, 0, or -1. And that allows me to basically say, if you give me a height displacement y, I can construct these dy's, I can find the betas, and then I can sum around each column, sum around each of these cells, and I can say, is there a dislocation here or not? So this is actually very similar, right, to what is done in DXA. Right. DXA just does this. If you give a point cloud in general, constructs these reference and tries to work out whether there is in fact a curl around one of these cells in the Delaunay tessellation that was talked about yesterday. So this is just a 2D version of this in some sense. So one thing to note is that I haven't told you what to do if you get an integer plus or minus 1/2. So there's a slight ambiguity here because I should decide whether I should round up or down there. And actually I'm not going to tell you what to do because actually that is kind of the case where I'm kind of between having a dislocation between two different adjacent sites. And actually I want to think about that if I want to consider changes of dislocation position. So we'll leave that for now, but just to note that there's an ambiguity here. So the work that I did in my thesis was basically to show that under various assumptions, let's leave it at that, there are local minimizers of the energy that I wrote down that contain dislocations. So if you give me where you would like to put dislocations, then there are some criteria about the separation between those dislocations under which you can then say there exists a local minimizer in this energy. So it can really prove that actually this energy can contain dislocation states using this notion of what it means to have a dislocation present. We can say various things about them. So in the original, in this paper, we proved some kind of global stability in an infinite lattice. Then we thought about finite domains and so forth. And I also wanted to highlight, so I'm not going to talk about this in too much detail, but if you want to know more about antiplane lattice models, you should talk to Maciek, because he spent a long time thinking about this in the case of mode 3 fracture as well. So really carefully doing some analysis for a model of mode 3 fracture, where various technical details become much more complicated because fracture fields are much slower decaying. But yeah. Okay. So that's those results. So that's all very well, but I promise you dislocation dynamics, not dislocation statics, and I've just told you about statics. So I've told you that there are local minimizers for dislocations in this lattice model. And so what we now know on the basis of what I just told you is that there are many states, many local minimizers that contain dislocations, right? This is well known, I think, for lots of things, right? This is what James was talking about the other day, James Commode. You have local minimizers that you can identify in molecular models that contain dislocations, and you want to look at barriers between these states. And so in this toy model, we really know that they're all there. We can prove them even in an infinite lattice. So it's an infinite dimensional system, not just finite dimensional. And so the point is that if there are such local minimizers, then the only way that you can move out of those local minimizing states is either you need to apply some force to change the energy landscape, or you need some thermal activation. So you need some energy to come in from somewhere else to actually get you out of one of these local minimizers. And so that's the inspiration for that is, again, came from talking to people at IPAM, I would say, is really I learned about kinetic Monte Carlo models here. And so I started thinking about whether we can formulate a kinetic Monte Carlo model starting from what we know about this dislocation model. And so in kinetic Monte Carlo models, the typical assumption is that you have some harmonic transition state theory. So you say that the rate to escape from some local minimizer is basically of this form. So there's some timescale factor that's called the entropic prefactor sometimes, but this really tells you the timescale that things occur on. And then I have an exponential of the energy difference to climb up out of the state, divided by the kBt, so the thermodynamic beta, which is the inverse temperature, and that gives you kind of an additional factor in how quickly, on average, these rates happen. Okay. So in this model, what are the states? So here's a picture. So the idea is that perhaps I have some section of crystal that I've carved out, and I know that I can put dislocations down in various points in these triangles, and they can have either Burger's vector +1 or -1. And then a state might look like what I've got on the right. So I've got 3 dislocations here living inside some finite volume. And then the transitions look like what I told you. So they should be basically when, or close to the point where the dislocation is kind of in the process of moving from one cell to another, and there will be some final state where I've moved completely into an adjacent cell. So I know that in general in BCC, there's some physics that I didn't realize because I was a math student. So in the sense that there are hard and easy cores, and actually the transitions are a little bit more sophisticated than are in this toy model, but I think a lot of stuff would still go through even if you work with that. So you would probably get transitions between this state and being here and so forth, but we'll come to that. Okay. So the idea is that we have these states that are parameterized by where I put the dislocations down, and then I can think about the kind of barriers between these states and try to build that into a kinetic Monte Carlo model. So as I said, it's a theorem that these minimizers are parameterized by dislocation positions. And in fact, the nice thing in this model is you can say even more. So energy barriers for dislocations that are sufficiently far apart can actually be characterized. So we can really say in some version of this toy model that the energy difference to escape from this state being here and moving to here is exactly of the form some constant energy minus some other constant times the peach color force dotted with the direction that I move. So this is really the work done against the peach color force. And the peach color force, if you don't know what that is, it's basically a continuum theory prediction of the force that acts on a dislocation. So it's really something that is completely continuum theory based, right? The original derivation of this is really about work done by moving dislocations. They were thinking in a linear elastic medium, but actually, it works in any medium. So what you really see is that basically there's if there were no peach color force, so if there's no stress acting, then there is basically just a barrier which does not depend on the stress because I'm in a local well and is kind of isotropic in the sense that whichever direction I move in this lattice, I pay the same energy cost to escape. But then the peach color force, so the continuum stress, actually tilts this barrier in different directions, depending on whether I should be. So it makes it more likely that I move in a direction that will lower the energy, in some sense, the continuum energy. And so that allows us to basically say that there's really something, it's a nice connection between this very discrete theory and the continuum theory that people already know. And then there's always error terms because this is a lattice model, so there will be higher order terms. And this, you should think of this h as really being, if I scale it with the relative distance between dislocations. So if I take the lattice spacing divided by the relative distance between dislocations, these error terms will be small. So yeah. So this is a leading order, this is small, and this is smaller in some sense. Okay. And so that allows us to postulate a kind of kinetic Monte Carlo model, which is that I move with some constant rate, but tilted in some sense by the peach color force that acts. So if you give me where the dislocation positions are, I can predict the peach color force using continuum theory, and that gives me a tilt on the rates locally. And so that's something we can do and build a kind of random walk model on a lattice. So in this picture, I've got squares. I can do this with squares or triangles. It doesn't really matter what the lattice is, but I can build a lattice model in this way. Okay. And so now I've got basically a random walk model for the dislocations on the lattice. And if I have, say, n dislocations, they're all going to interact because they all induce stresses that will affect each other through this F here. And so I have kind of an interacting random walk for however many dislocations I choose to put down. Yep.
So does this generalize easily for three-dimensional curves? Curves in 3D?
Does it?
One-dimensional curves in 3D.
One-dimensional curves.
I mean dislocation loops.
You mean loops in general. So I don't think it generalizes easily. I believe that something like this should be true in the sense that like you can probably use the Ritz-Ortiz model, which is a fully 3D model, to actually think about this, but it's not something I've done. But, yeah.
So you have an epsilon in the denominator of the random transition, which is the lattice spacing.
So the epsilon is a length scale ratio, so it's dimensionless. Yes. So in some sense, I wouldn't read too much into what I've written here. It's the scaling that makes you get the right answer when you... So you need to take some non-dimensional combination of things to a limit. And it so happens that this is the right non-dimensional combination of things. Yeah, like I say, don't read too much into exactly what this factor is, but I can give you the gory details later on if you want. But yeah. So yeah, there's some freedom. We're going to basically rescale time, space, and temperature all at the same time in a second. So there's a very complicated parametric choice to make. But yeah, I'll come to that. Anything else before I move on? Yeah? So what I mean, I can't remember if I've spelled this out very explicitly. So this F here, secretly F is a function of all the dislocation positions. So right, F is, the peach color force is something that comes from the stress field acting in the material at where the dislocation is. That stress field is induced by the positions of all the dislocations and any external forces you would apply. So really, F is a function of all the positions of the dislocations and any stress that you apply. And so that's how the interaction happens. So it kind of, you put the dislocations down, you generate a stress field, that gives you a prediction for the peach color force, and that will tilt the potential. And as you move them around, the F will change, and therefore they interact in that way. So they interact in kind of a far-field linear elastic way. Okay. So the question that I ask myself is, so I've got some random model, great, but I guess if we were trying to really go towards discrete dislocation dynamics, we want to understand whether we can take the lattice out of this equation. Maybe equation is the wrong word, but take the lattice out of this model and pass to some continuum limit. And so we did this by various different methods. So the thing that I thought about first is to go to really low temperature. So that means inverse temperature should be very large. And there, actually, you can think about the random walk, so this interacting random walk, and think about a large deviation. So what is a large deviations principle? So a large deviation principle holds whenever you have a random process that kind of satisfies something like the following thing. So it says, suppose I have random variables xn, and by random variables I mean it could really be random trajectories of some dynamical system. So such trajectories satisfy a large deviation principle if in some asymptotic limit where I pass n to infinity, so n should really just be thought of as a sequence of these random variables, then I have something like the following holds. So the probability that the random variable or random trajectory looks like some trajectory little x looks like the exponential of minus n times the sum j, where this j is the rate functional, I won't go there yet, and it kind of quantifies the probability of observing a particular value, x. So if I really think of trajectories, this j is actually going to turn out to be an action. So it's kind of related, if you were around for workshop 1, to what Steve Fitzgerald was talking about. This j is an action that kind of tells you how much energy you pay to observe a trajectory, and if I have very low energy or zero energy in this action, then I should observe this trajectory with very, very high probability close to 1. And anything else will be exponentially unlikely. Yes? N is just an index of a sequence here. So yeah, this is a completely generic statement in the sense like I take you can have different rates here. You don't have to have an n, you can have n. It should tend off to infinity, but the n here isn't super important. The point is somehow that it just concentrates right around minimizers of j as n tends to infinity in some way. Okay, so the theory of large deviations has been developed over a long time. There's a book that's a challenge to read, let's say, but is very, very general about convergence of Markov processes in general. So this book contains a huge amount of stuff. It's just you have to dig through to find out exactly what's going on, and so it took me a long time to read this book, but it is really powerful, the theory that they develop. And so what they show is that I'm not going to say too much more about this because it would be a long discussion in itself. So you have some semi-group that generally generates a lot of these processes, and there's a certain kind of nonlinear semi-group that you can form, and if you have a convergence of these nonlinear semi-groups, then that automatically gives you large deviations principles. And that's what the theory that Feng and Kurtz developed says. And so if you can use that theory, then you can prove one of these things kind of automatically. It turns out that if you, the nice thing about how they do this is the nonlinear semigroup allows you to basically characterize the rate functional in a lot of situations. And in this case, like when we have really some Markov process, it turns out that the rate function can actually be expressed as what I said, an action. So somehow the trajectories that I should observe for some continuous time Markov process will converge to something that minimizes this action. And so that's nice because it says that the trajectories concentrate around some physical principle in some sense, the minimizer of some physical action. Okay, so that was very general and maybe not that clear because I was skirting over a lot of details, but let me now give you some idea of how you can use this in the case that I've just talked about. So we're going to focus on the low temperature regime. We're going to focus on the regime where the lattice spacing is small relative to the domain size and the spacing between the dislocations. So that's what epsilon is. So epsilon is small, beta is large, and because I'm going to low temperature, of course, transitions are going to become rarer and rarer, right? I'm going to escape at slower and slower rates from being in a local minimizer. So that means that if I want to observe something on some reasonable timescale, I have to speed everything up. So the observed time needs to be scaled longer as I lower the temperature. And so, in short, if I do that in the right way, so I form these groups and pass the limit in such a way that these both stay finite, then I will get a large deviations principle. And the way you should think about these groups, or the way I would like you to think about these groups, is in some sense that A is going to give you some kind of macroscopic velocity of dislocations. So you want this to be finite. So if it's 0, then I don't see anything happen. If it's infinite, everything happens too fast. So I need to scale it just right so that I see things happening at a steady rate. And then B is kind of the ratio between the energy that you've got available thermally to the work that's done by Peach-Color force. And if this is too large, then basically you won't see anything happen. And if it's too small, you'll see everything happen too fast. So if you tune these exactly right, and by exactly right, I mean any value between 0 and infinity strictly, then you will get something right. So this tells you the asymptotic regime in which you observe a large deviations principle. And in that regime, what you find is that actually the trajectories satisfy one of these actions. I'm not going to give you the gory details, but you actually get that the trajectories, so this is now xi is the position of a dislocation in this, so it's a line cutting through a 2D plane. So this is a point in the plane where it cuts through. The velocity of the dislocation is given by some mobility function of the Peach-Color force. So here I'm really making explicit that this Fi depends on all the dislocation positions. And Fi is really coming from linear elastic theory. And so the mobility function, interestingly, depends on A and B, these two parameters that I identified before, but it also depends on exactly the lattice structure that you put in. So in the 2D lattice. So I did this, so the true one for BCC, or the closest to the truth, is this one, because I really have a triangular lattice when I project onto 2D, but I also did it for these other lattices, just because it's actually slightly easier, as you can see from the form of this thing here. So yeah, the point is that this is not just a linear mobility, this is some non-linear mobility that you observe at low temperature. So that's, I think, nice. Whether this is valid, of course, is a big question, right? So is beta really that small? That this is the right regime to be thinking about these things. So that's the next question to really ask is what happens if I don't have beta being really tiny? So, really large, so temperature really small. And so then we can start to think about kind of something that's more diffusive. So in what I showed you, what this theorem says is that for temperature really low and where I scale the parameters all correctly, I get some deterministic evolution, or very close to deterministic evolution, driven by this set of nonlinear ODEs. But of course, if temperature is high enough, I will see some diffusive behavior. And so that's something that I studied with Patrick Van Meurs and Marc Pelletier. So we thought about actually the higher temperature case. And so there, what you should kind of expect is that rather than some ODE law for the relaxation of the dislocation positions, well, it's probably likely that I should still see some noise present. And so I'll have an SDE. And so here, this grad E delta is actually the Peach-Color force again. I've just written it in terms of the gradient of some energy functional, which we can actually write down. And so, yeah, we've got a random walk model. We've got an ST model that's kind of at the semi-discrete level. So I've now got points in 2D that are moving around according to some SDE. And actually, we can go even further, because this is kind of what I was alluding to at the end of yesterday when in the question I asked. There's also a kind of mean field theory where I can start to think about very many dislocations all interacting together and what the kind of density of dislocations should do in that case. So we've got these different levels of theory, and we want to potentially connect these together as well. Yes?
So here the nonlinear mobility is no longer there.
Yeah, the nonlinear mobility is no longer there. So the nonlinear mobility only arises really because you're going to really low temperatures.
Okay. But it's related to the lattice that you...
Yes.
Okay, so in this regime, like the lattice doesn't really matter.
Yeah, the lattice doesn't really matter anymore. So it does come in that it basically comes in as it's a factor in the diffusion coefficient that I'm hiding. So if you have more directions to diffuse in, you go slightly faster, but it's just a scale up or down. Yeah.
In the low temperature case, would you not have you're saying you'd have an ODE for the mean field. The mean field model will be a first order PDE, or in the low temperature case when you don't consider the diffusive terms?
In the low temperature case, so that's actually what these results are. So in the low temperature case, so where I have infinite temperature, I basically cross out this term and I still have a first order in time, but a kind of mean field evolution equation. So you have basically an interaction. This is basically a convolution of interaction multiplied by kind of mass of dislocations, and then you're transported by that, in some sense. But the higher temperature just adds this diffusion. So it's actually, the nice thing is it kind of comes in the most obvious way you would expect. You just get a beta inverse Laplacian, like nothing complicated happens. It's the same as this model. It actually, in some ways, is easier to analyze the thermal model than the deterministic one, because this is, without this term, this is a very nasty PDE. So this work is hard that people did. I mean, what we did was also hard, but I would say this is in even more analytically tougher stuff, because you don't get the nice regularization that you get here. Okay, so I am way behind schedule, but that's fine. Okay, so what we did with Marc Pelletier and Patrick Van Meurs is to basically study these two theoretical limits. So formally, we know that we might expect that if I take the lattice spacing to 0, I converge to some kind of SDE model, or approximately, at least statistically speaking, I converge to some SDE model. And if I take the number of dislocations to infinity, so I kind of take the density, I take a very large number and scale space in the right way, then I should pass to some me-field model. And then if we can do both of these together, then I would get the convergence directly from here to here. And so then we asked ourselves, can we connect these models rigorously and estimate errors? And the short answer is that we can. So this theorem is basically considering just n fixed and epsilon being small. So actually, this is a quantitative result in the sense that it's not, excuse me, I'm not really taking epsilon to 0. I'm taking epsilon close to 0 and showing that the solutions of these things are the same. So what does it say? What you should see is basically if I take the random walk for n dislocations on a lattice spacing of epsilon, and I take the SDE model, and I compare the laws at time t, evolving from initial conditions, initial laws, which can be random or can be deterministic, then this is how it behaves. So the error in law in L2 is bounded by the initial error plus something that scales like the epsilon squared, basically. So you could do other measures of error. This is L2 of the law, which is actually set on a very high dimensional space because things work out nicely, but you could probably prove other estimates of this type. But what it does show is that as epsilon goes to 0, if this error in law at initial time goes to 0, then actually the evolutions converge in this sense. So yes, we can assume, we can take this initial error to be order epsilon squared as well if particles are initially identically distributed. So if I put them down wherever I like, which would be exactly what you would expect because you can't distinguish dislocations. If you just look at them, they, if I swap their positions, it looks exactly the same, so I shouldn't really do anything else. Then I will get the same order of error in these two terms. So how do you do this in practice for the mathematicians who might care about this? So basically, we work with the Fokker-Planck operators for these two processes and show that the random walk Fokker-Planck operator is a weird finite difference approximation of the Fokker-Planck operator for the SDE. So not one that you would actually want to use numerically, but you can basically use ideas from numerical analysis to show that this convergence holds and use Gromwall in a kind of standard way. So there's a fair amount of work in going in here, but fundamentally that's the key idea. And as I say, I'm sure that you could do things in other metrics if you were so minded. It's just that we chose to do L2 because you can do this stuff most easily there. The other thing that we did, which is more down to Mark and Patrick, I must say, is to then also think about the convergence of the SDE, or the error between the SDE, the law of the SDE, and the evolution of this mean field model. So right, the mean field model is a PDE model that's deterministic, but what we showed is that the law of the SDE for n lots and lots of dislocations behaves very close to the solution of this Fokker-Planck equation. In the following sense, so this you should just read, if you don't know what this means, as the expectation of the error between the solution to the PDE and the empirical measure of the solutions. And this is for those that know what that means, this is the dual Lipschitz norm on two measures. And this behaves basically like if you ignore the log, 1 over square root n times some constants. So how do you do this? You do this basically by coupling. Again, for those that this means something to, you basically define a proxy that's driven by the solution to the mean field equation and drive that, and then you use some techniques that are well established in interactive particle systems to control things. And you prove that. So the nice thing is that actually, because we've got these two quantitative error bounds, we can stick them together and show that the random walk is in some sense close as epsilon goes to 0 and n goes to infinity to the solution of this mean field equation. And as a bonus, we could do it the other way around if we wanted. So we also showed that there's a mean field discrete model on the lattice that this, you can pass the n to infinity first, which doesn't really make sense because I'm putting an infinite number of dislocations into a finite grid. But you can still make sense of the error between these things and then pass epsilon to 0. So in some sense, this is a nice commutative diagram. I can do either of these limit processes and I get the answer. And I do not believe that because we concatenate these things, we're probably getting a sharp error bound on what's going on here. But, you know, it's nice to be able to do this. Okay. So I have about 7 minutes left. So I think I'm not going to get all the way to discrete dislocation dynamics, but I wanted to tell you about something else that I did with Christoph and Julian Braun, who was a postdoc with Christoph at Warwick, which concerns kind of far field around defects. So what I've been talking about up till now, all of this stuff is based on really a toy lattice model where I just have nearest neighbor interacting columns in this screw dislocation case. So this is really a toy model. There's some, inspiration from physics, but there's not any really hard-coded physics in there. But as we know from what's being discussed here, we do need that physics in lots of cases. So we're now going to think about defects in more realistic models of defects. So let's go back to the start and start thinking about energy again. So I'm going to now allow myself to consider lattice displacements, more general lattice displacements, right? So the place I started was with these antiplane displacements, but now I'm going to allow atoms to move in 3D in general. And I'm going to assume or make the common assumption that is made when you write down a molecular dynamics potential, or you code up a molecular dynamics potential, that the site energy of this atom, this red atom, is local in some sense. So it only depends on some interaction neighborhood nearby. And so here, sorry, I should also make something clear. So L is some reference lattice position in this lattice lambda. So this is a three-dimensional lattice now. And I'm perturbing this by some displacement U, which is now vectorial. Right? We started, I had these columns that are reference atoms are shifted by some vertical displacement. Now I'm really allowing a three-dimensional displacement in general. And so because of all the things that have been discussed already at this workshop, we know that VL must depend only on displacement differences, or equivalently on position differences, right? That's exactly the same thing, because this is just a different way of writing that thing. So the local site energy for this atom, the interaction of this red atom with its environment, must only depend on the difference in displacement between atoms in this area. Okay, and so what we will do is formally express the potential energy of all the atoms in some lattice by summing the site energies and basically writing du to express the collection of displacement differences that go in here. So this could be a very complicated function in general, and we will try to keep it that way. Okay, but just to give you a really clear indication of the idea, if this is a little bit confusing, basically if I really had a pair potential and phi, so really think Leonard-Jones, then the site energy might look something like this. So I have rho some interaction directions in a reference lattice, and then I take the displacement differences, and this is basically the same as taking the moved position differences and summing them up. And this interaction radius could be larger than the cutoff of the potential, so I have no issues with like neighbors moving in and out of regions, for example. But as long as it's finite for the purposes of our analysis, that's all that matters. So I could take it much larger than the cutoff radius, so I'm allowing quite significant rearrangements. Okay, and as so even with this antiplane lattice model, what's obvious is that because there are many local minimizers, this energy, or any energy like it, is going to be a massively non-convex function. And if I really take this in the infinite lattice, it's defined on an infinite dimensional space of displacements. And so then what we're going to do is study equilibria of the system, so in the way that we did. And so seeking displacements at which forces on each atom vanish. And that's the same as seeking critical points of the energy, right? So that could be local minimizers, it could actually also be saddle points. And so one way to do that, right, is to kind of fix the atoms at the boundary and allow the red atoms inside to vary and relax. Because we obviously can't solve the infinite dimensional problem, but we can start to think about what happens as I take this red region larger and larger. Do I actually converge to something? Am I close to the kind of ground truth of the infinite lattice or not? And we can ask, how should the boundary conditions be set to achieve an efficient approximation? Yep. 2 minutes left. Okay. So let's skim through this. So basically, continuum elasticity theory comes to the rescue again. Yeah, I'm never going to get through all of this. So let's just skip to the punchline, which is, so it turns out that if you do some clever linearization in the far field and work things through and use some Fourier analysis, then you can actually show fairly good quantitative properties of what the defect fields in the far field look like. So the point is that because we know that the strain fields around defects decay, that's what we see when we look down a microscope and see that they decay, as was discussed yesterday, we can actually guess that that might be the case, linearize in the far field, and use some clever techniques to work out how to decompose that far field into pieces that have ever-increasing decay. So the leading order term always looks like the continuum linear elasticity solution that's been established probably in the last 60 or 70 years. And then we can add correction terms that decay faster and faster. And I think, given time, I will zoom all the way through all of this other stuff and come right to the end. So as I've said, I've showed you various toy models and maybe not so toy models. And I think the nice thing is that these do yield interesting insights that maybe can be tested then with more serious models and to work out, does this tilting actually happen for barriers? If I apply some stress or strain, what is the relationship between those things? Can that be used in some higher order continuum model? And I think, as I would have said in the latter part of the talk, I think there's still a lot of work to do to confirm that we're accurately passing information from the atomistic scale up to DDD and onto crystal plasticity models. And there's various references there. So thank you very much.